Bueno, muy buenas tardes a todos y todas. Bienvenidos a este seminario institucional. I'm going to introduce you in Spanish and then Matthew is going to talk in English. So thank you very much, Matthew, for this. Sean bienvenidos a este seminario institucional. Como saben, tenemos un seminario institucional al mes y también tenemos un ciclo para invitados especiales. Y en esta ocasión, pues tenemos el honor de que Matthew Haney va a venir a platicarnos sobre su experiencia en Alaska y voy a dar una breve introducción sobre Matthew. El doctor Matthew Haney es egresado de la Colorado School of Mines, ahí colaboró con Roel Snyder. Fue postdoc en los laboratorios Sandia, ahí con David Aldrich, y en el postdoc Mendenhall del USGS en el Alaska-Volcano Observatory. Esto fue del 2005 al 2009. Fue profesor en la Universidad de Boise y ahora es director del Observatorio Vulcanológico de Alaska en Anchorage. Su área de investigación cubre la interferometría, la sismología volcánica y el infrasonido. Es sismólogo de volcanes, que trabaja, como lo mencioné, en el Observatorio de Volcanes de Alaska. Se centra en la interpretación de la sismicidad en los volcanes con el objetivo de proporcionar al público mejores pronósticos y evaluaciones de los peligros de los volcanes. Una parte importante de su investigación incluye la interpretación de las ondas sísmicas en la Tierra y las ondas sonoras en la atmósfera para detectar disturbios volcánicos, obtener imágenes de la estructura volcánica y dilucidar la dinámica de las fuentes volcánicas. Matthew ha publicado 143 documentos y cuenta con un índice H de 30 en Scopus. Thank you very much, Matthew, for your visit, and we will be hearing your seminar, and then we will keep the questions for the end of your talk. Thank you very much.
All right. Muchas gracias. Thank you. And I thank you so much for giving me the opportunity to come here to give the talk today. And also special thanks to Paco Sanchez-Sesma for inviting me and taking such good hospitality at your house. Thank you. So I'm excited today to talk about volcanoes, and I'm excited to be here because I know Popo is very close by, and I'm excited to go to see Popo next week. In Alaska, our volcanoes are also very active, but they're very far from where I live in Anchorage. Here, it's so interesting to see Popo so close. So for example, here's one volcano on the title slide. This is in the Aleutian Islands. It's called Great Sitkin, and here is it's having an eruption and making a lava dome at the summit. So I'll talk about Great Sitkin today later in the talk. First, I just wanted to say at the first slide, acknowledgement of the lands of Alaska. I'm not originally from Alaska. I've lived in Alaska for 15 years, but the active volcanoes of Alaska, are on the lands of the indigenous people of Alaska, which are Dena'ina, Alutiiq, and Unangan people. So the volcanoes are on their indigenous lands. Unangan are the indigenous people of the Aleutian Islands. All right, so the subduction zone of Alaska it's very active. There's always seems to be an eruption somewhere in the Aleutian Islands. So right now, I've shown we have a color code system of activity. I'm showing green, yellow, orange, red. And so right now we have 4 volcanoes that are elevated above green, which is just background. So we have 3 that are at yellow, west to east, Garaloy, Kanaga, and Shisholden, and then 1 at orange. Orange means low-level eruption, and red is major eruption. So currently, Great Sitkin is having an eruption, but low-level. So it's, lots of volcanoes, 54 volcanoes in the arc. This is where I am, Anchorage, Alaska. And we average many eruptions per year in the Aleutians. It's very sparsely populated, so the main hazard that we look for is aviation, these airplanes that fly over the Aleutian Islands, and warning them of any ash clouds from eruptions. Because even though it's sparsely populated, not many people live out here, over 50,000 people per day fly over in airplanes. So lots of people in the skies above Alaska. So today's talk, I'll just talk about two volcanoes, studies at two of the volcanoes. The first one is Trident. Here, it's near the Katmai volcanoes. Here's where I am again, Alaska, Anchorage. And I'll talk about a new method of earthquake location applied to recent earthquakes. And then second part of the talk will be Great Sitkin, looking at small changes in seismic velocity during the eruption that we saw, that lava dome at the top of the volcano. So, how do we measure the volcanoes in Alaska with seismometers? It's our seismic network. So we have over 300 seismometers in Alaska-Aleutian Islands, operated by Alaska Volcano Observatory. So here's at every volcano that we monitor, it shows a diagram of where the seismic stations are, so we can predict eruptions. And this is also showing, in the past decade, our instrumentation became modern. So they call it A to D, analog to digital. So now, over the last decade, all the instruments are modern digital seismometers. So it was a vast improvement in the network. But you can see, because of the distances that, most of what we do at AVO is, flying out to these 1,000 kilometers to the volcanoes. The logistics of the field work is very difficult in this area. So a lot of the time is spent just planning the field work, doing the field work. That's always in the summer. And then in the winter, starting planning for next year. And with all those seismometers, we measure earthquakes every day in Alaska. So this is a plot. Alaska Volcano Observatory started in 1989. And since then, here's the number of earthquakes we locate per year. So, as more seismometers are deployed, we measure more and more earthquakes. So last year, these are all hand located by an analyst picking P and S waves. We located over 18,000 earthquakes. The total is now over 179,000. So every day we have an analyst picking earthquakes, because even though there are automated methods and we use those too, still the highest quality location of earthquakes is from human analyst picks. Although maybe that will change in the future. So that's the number of earthquakes per year. Then if we look at earthquakes per month that we locate, then you can see times of high levels of earthquakes, and those are usually at times of eruptions or intrusions at volcanoes. So you can see all the different swarms at different volcanoes that occurred. In the past year, we had big swarms at Tanaga and Katmai that resulted in over 3,000 earthquakes in a month, which means 100 per day, picking by hand. It's a lot of tedious work. And then here I've highlighted, not all these swarms, when a magma intrudes onto the volcano, eventually erupt. Sometimes it stalls, but the ones in red eventually went to eruption. So some of the most famous eruptions in Alaska in the past 30 years, Augustine and Redoubt, about some 15 to 20 years ago. So these are this is the main workhorse of volcano monitoring in Alaska to detect these earthquakes. So this is our earthquake catalog, just some information. So since 1989, we locate these earthquakes. We use a code that's used widely called hypoinverse, very standard earthquake location code. But a detail is that hypoinverse, when you locate the earthquake, the initial guess is always at 5 kilometers depth below the coordinates of the closest station. So if the earliest pick of a P wave, the closest station, the initial guess is 5 kilometers below that station. That's the initial guess. So and the origin time would be 2 seconds before that pick. So it's a very crude type of initial guess. So the first part of this talk, I'll talk about an improved way of making an initial guess. And that is called the Bancroft algorithm. So here I'll talk about how to adapt this algorithm to make a better initial guess than our usual initial guess. Now that algorithm, I'll talk about it on the next slide. It makes some assumptions that we want to get past, which it assumes homogeneous Earth, one velocity, and it was designed for electromagnetic waves. So it just uses one type of wave type, the EM wave, speed of light. Whereas in seismology, we have both P and S waves. So the first part of the talk will be about how to make this algorithm have different velocities and use both P and S waves. So this is the Bancroft algorithm. Some information. This is the original paper by Bancroft. So it was originally used to get an initial location for locating a GPS receiver from satellites. So it uses the speed of light, a single velocity. But then in a paper about 10 years ago by Gomez and others, they cleverly showed that it's the same type of problem as locating an earthquake. Except instead of satellites, you have seismic stations, and instead of a GPS receiver, you have an earthquake. So it's the same type. It's an algebraic solution of the earthquake location problem. But like I say, it has some simplifications that I'll talk about. So here's, if we're going to use it for earthquake location, then here's some 4 cases of earthquake location. All the picks are P waves. All the picks are S waves. Then there's a special case where for every time you pick a P wave, you also pick an S wave. And then there's everything else, which is the usual most of the time. That sometimes you pick a P wave, but you can't see the S wave. Or, this is the most general case I'll talk about today. These are special cases. So these ones, the top 2, they can be handled by the normal Bancroft algorithm because it's only one wave type, either all P or all S. This is a special case I won't talk about, but it simplifies. And then this is the most general case. So the one that we want to do when we're locating earthquakes. Okay, so at first I was going to talk about the standard Bancroft algorithm, and then I'll talk about the improvement. So these are, travel times, P, S wave. So this is the distance from an event at these coordinates in the seismic station at I. So the P wave would be the distance divided by the P wave velocity plus the origin time. S wave, same S wave velocity, origin time. So the standard Bancroft algorithm is just for EM waves with one velocity, so it can be applied to either P or S. So here I'll show it for P waves, just to illustrate the standard algorithm. And this is a reminder to me to say, for this first part of the talk, there'll be some math equations, and I don't expect you to understand all the details, but I just want to convey some of the, what's happening broadly, but don't, it's a lot of equations, so don't think that all the details are important. So the standard Bancroft algorithm, so this is the one for just P waves. If we manipulate that travel time equation, and then we use this matrix, here I'm calling it M, which is called the Minkowski matrix, named after Hermann Minkowski, a colleague at the time of Einstein. It uses a special matrix that has 4 by 4, 1, 1, 1, minus 1. So you have to use this matrix to solve the problem. And when you manipulate the equations, you get to what's called this GPS navigation equation. So there's the source coordinates where the earthquake, the XYZ of where the earthquake is, the origin time of when the earthquake happened, and then the P wave velocity. And then you have these other matrices that I'll talk about on the next page. But this is the unknowns we want to find. And then this quantity, E of P, also has the unknowns, which is the coordinates of the earthquake and the origin time. But there's an inner product of these with the Minkowski matrix. So it's the Bancroft algorithm is the way to solve this GPS navigation equation. So if we go to the next slide, here's the details of this navigation equation. So they use this in GPS as far as I understand. It's a very standard equation. So here's our 4 by 1 vector of unknowns. We want to find this. Unfortunately, there's also our unknowns are also in this E of P, a quadratic in terms of the unknown. And then we know this. This is based on station locations and P-pics, so we know that We know this also, station locations and p-pics. And then this is just a vector of ones, which is the number of p-pics. So we know everything here except this vector and this quadratic inner product. So what Bancroft showed was how to solve for the unknowns. And the way that's done is first you take that matrix WP and you pull it over on the right-hand side. So here's our unknown vector, and then here's the WP. I'm making a shorthand notation now. So here's the unknown vector. Here's that quadratic in terms of the unknowns, and then these other things that we know. So then finally, to this, we take the Minkowski inner product of both sides of this equation. So we take that matrix and the vector and we apply it from the left-hand side. And what you end up is a quadratic equation. So it's quadratic in terms of this quantity, EP. So there's the linear first order, second order term, first order, zeroth order. So then this equation can just be solved like by the quadratic equation. There's two solutions. And so from those two solutions, you find out which one is physically meaningful. So one of the two solutions will have an origin time after the pix. So that one is not meaningful. So you look for the one that has the origin time before the pix. That one is the real one. So you just solve a quadratic equation. It's very simple to do. And so here's the review of how you would locate an earthquake with just P waves from the standard Bancroft algorithm. So you form this vector and matrix from what we know, station locations, arrival times. You solve a quadratic equation for this quantity. You find which one is physically meaningful. And then from that one, you substitute that physically meaningful one into this here. So now you know this, you know this, you know this, you know that. You don't know this. Well, you know VP, but you don't know X or T0. So then you just solve that and you have your location for the earthquake. So it's an alternative way of locating earthquakes, but it doesn't require an initial guess. It is giving the initial guess. So that's its advantage. Okay, so one question that comes up is, in the standard one, it's electromagnetic waves. So you just use the speed of light for GPS location. But in the Earth, the velocity is not constant. It changes with depth. It usually goes up with depth. So what can we do? So it assumes constant. What can be done for an increase of velocity with depth? This is from the Katmai volcano, VP. You can see it starts at 5 kilometers per second and then goes to, at 30 kilometers depth, up to almost 8 kilometers per second. That's in blue. So what we do here is take the root mean square velocity. So it's an average down to a certain depth. So that root mean square is shown here. And then that's a good approximation for a homogeneous medium at that depth. And so then we apply the inversion at every depth using the different RMS velocity. And then when the inversion gives us the same depth as what we're considering, then that's the depth of the earthquake. So you scan down in depth to find what is the best. So it's a consistency. The velocity at that depth is the same as the inversion is giving back for depth. So that's how depth is done. So that's one of the additions to the Bancroft algorithm. Then the other one, so this is the last section of equations. So this is, for now, looking at how can we do it with both P and S waves. Okay, so, before we had this equation for P waves, you can have the same equation for S waves, except now you have ES instead of EP. You know these vectors, you know that. You have the same unknowns, X, origin time. Here it's using S velocity instead of P velocity. So now we want to go through and see how do we use both at the same time, because that's what we do to locate earthquakes. So where EP and ES are these inner products of these unknown vectors with the same Minkowski matrix to give EP and ES. So there's a few steps, and I'll just go through them, and then we'll look at the results. So the first thing we do is we break apart these WP and WS matrices into the spatial coordinates, which is 3, and the time coordinate, which is 1. So then if we break up the matrices, then those two equations from the previous slide look like this. So here's XR, T0, EP, ES. So we can rewrite these two equations in a matrix form in two different ways. So these are kind of the same equation, but we write them in two different ways. So up here, we have this partition matrix where we have the ratio of S and P velocities into this lower right part. Here is XRT0 VP. And then for the other one, same equations, but now we rewrite them in terms of XR and VS times T0. And so then we use the VP-VS ratio up here. So it's the same equation written in two different ways. So I call these two matrices UP and US, and they're linearly independent from each other. They're different matrices. So we want to find these two unknowns here. So it's just how to couple these two for P and S waves. So then the next step is we take those UP and US matrices and invert them, bring them over to the right-hand side to isolate this unknown vector and this unknown vector. So I call these QP, these pseudo-inverses of UP and US. And then we have to further break apart the QP and QS matrices. So here we break them apart into the number of P picks and the number of S picks, like this. So then if you write it, now again, the unknown terms here, now we have EP, ES times these different matrices, also here EP and ES. So we want to know this, EP and ES. So the way to do it is just like before, we take the Minkowski inner product with these two equations, and we end up, lots of equations. So we use a shorthand notation, but the important thing to see here is now we have two coupled quadratic equations. So the two unknowns are EP and ES. So the linear term, EP, EP squared, ES squared, cross term of EP, ES, then linear EP, ES, 0th order term. So it's two coupled quadratic equations, which themselves can be reorganized into a single quartic equation, so 4th order. So this is how the whole Bancroft algorithm is made general for P and S waves. So now we have to solve a quartic equation. Okay, so that's finally the recipe for the generalized Bancroft algorithm. We form these matrices and these vectors based on what we know, station locations and arrival times. Then we solve a quartic equation for EP or ES. You can choose which one. And then from the 4 solutions, we have to find the physically meaningful one. There's some details there. And then finally, once we find EP and ES, then into one of these two equations, we substitute them and solve for the unknown. So it's an alternative way of solving for earthquake location. And it can be used as an initial guess for the more refined final earthquake location. All right, so with all that details, now we apply the new method to Trident Volcano. And this is a volcano that has been last active in 1950s, 60s, 1970s, small lava flows. It is the location of the largest eruption of the 20th century, which was at Mount Katmai in Nova Rupta. That was in 1912. That was a VEI 6. So it's very close to the Valley of 10,000 Smokes in Alaska. And so we monitor it with a local seismic network and INSAR from space satellites. So in the past few years, there was an intrusion at Trident. That's the volcano here. Here's Trident, here's Katmai. That's the caldera that formed in 1912. Valley of 10,000 Smokes, all the ignimbrite that was erupted from Nova Rupta spilled and filled the valley. So here you can see Trident has new lava flows. You can even see in this image. So it's had activity over the past few years. It started in August 2022. Lots of earthquakes. Earthquakes up to magnitude 4, which for a volcano is large. So now I'm going to apply this new way of locating earthquakes to 500, a little over 500 earthquakes from July 2023. So here's some information about the earthquakes. All the arrival time picks are from the comprehensive catalog of the USGS, so you can get them from a web service. We use that CapMy velocity model to compute the RMS velocity versus depth, and then we compare it to the catalog location, which for this purpose will be like the truth, and then also the initial guess of hypoinverse, which is 5 kilometers below the closest station. So this is, we're going to call this the truth. This is the other type of initial guess, and then what Bancroft is going to do. So here's a plot showing Bancroft versus the hypoinverse trial depth. So this is catalog depth minus Bancroft depth and catalog depth minus the hypoinverse initial depth. So what this is showing is that, with the usual hypoinverse initial depth, 5 kilometers, you get a bimodal distribution. And this is because there's deep earthquakes and shallow ones. And it's because the initial guess is always 5 kilometers. But you can see here with the Bancroft method, it removes the bimodal distribution. So it's trying to actually locate the earthquake, and it's removing that bimodal distribution. Here's looking at the epicenter, so the point on the Earth where the earthquake is below. So here's catalog minus Bancroft, and then catalog minus the hypoinverse initial epicenter. So the initial epicenter of hypoinverse will always be the closest station. So you can see here for Trident, typically the closest station is about 5 kilometers away. So usually the initial guess is 5 kilometers away from where it's located. But with the Bancroft, you're getting much closer to the epicenter. So it's much better initial guess than hypoinverse. Here also is the origin time. It's similar as the depth distribution, a bimodal distribution, because deep and shallow earthquakes that you mainly remove it to get a single distribution, which is scattered about 0. And then finally, this is the comparison of the fit. So the root mean square of the fit. So for the catalog, we require that it's less than 0.3 seconds in our processing. And you can see that for Bancroft, it's usually less than 0.3 seconds. It's usually about 0.2, but it's a distributed, but it's mostly getting into that area of a good fit. So as an initial guess, it's much better than the hypoinverse initial guess. And then finally, this is the last slide for this first section. There was a very interesting vertically migrating swarm of earthquakes at Trident in August 2022. So this is the catalog. You can see it started on August 23rd, and it migrated vertically. So this was an intrusion of magma underneath the volcano. This was the beginning of the unrest that lasted throughout 2022 and 2023. So there was this migration, and so this is the catalog, the final locations. But you can see with Bancroft, this is the depth plotted versus time. It also is able to get a good initial guess of that, initial estimate of that vertical migration of the swarm. So with earthquake locations, depth is usually the most difficult quantity to get because the stations are usually on a plane. But here you can see even with this vertical migration, we can see in both the final and the Bancroft method. So again, it can be used as a very good initial guess that can be subsequently refined with hypoinverse. All right, well, so that was the first section. Now the second section, which is on Great Sitkin, and then I'll wrap up. So at Great Sitkin, I'm going to describe the eruption here in the Aleutians that began in 2021. The previous eruption was in 1974, and we've been monitoring it with a local network since 1999. It started to have unrest in 2017, and then it took 4 years until it began its eruption. So it had a very long period of unrest leading to the eruption. So here's a picture from 1974. Somebody in the Aleutians happened to be flying around and took a photograph of the previous eruption in 1974, making a ash cloud. This would be about, I estimate, 6 kilometers, 5, 6 kilometers above the, we can't even see the top of it, but it was not a particularly violent eruption. Then I mentioned in 2017, it started to have unrest, more earthquakes every year leading up to 2021. And in 2018, it had what we call phreatic eruption, which is steam, water coming into the volcano and just blowing apart like a steam eruption, not a magmatic eruption. So here we saw it on the seismometers, and then also from this aerial image, you can see this streak of ash from the phreatic eruption. But this is not new magma, it's just the country rock getting blown apart. So this is in the buildup to the 2021 eruption. So here's our local network at Great Sitkin. So it's these 5 stations on the volcano. There's one on a neighboring island. There's another volcano up here called Kasatochi, which is active but not monitored by any seismometers. So we'll look at these 5 stations at Great Sitkin. Here's just showing again that lead up of the seismicity. So this is leading up to the 2021 eruption. There was lots of earthquakes up to magnitude 3.5 in 2020. And so it was very active, and then it, when it started to erupt, then it went quiet. No more earthquakes, very few. So this is just showing, here's the 2018 phreatic eruption, a lot of earthquakes that day. Then lots of earthquakes over the next few years. And then on May 26th, 2021, it had a Volcanian explosion. It was caught by a boat which was sailing by the island. Amazing that the weather was like this. It's usually cloudy and terrible weather, but they caught the eruption from the boat. And then after that eruption, that day there were a lot of earthquakes. Then it started to fuse a lava dome at the summit, and that was very quiet, no earthquakes during the dome extrusion. And that dome extrusion started in August of 2021, and it is continuing today. So it's been going on for 2.5 years. It's a very large lava dome. It's the one we saw on the first slide. Okay, so for this, I'm going to apply a method called coda wave interferometry, which uses the coda, the multiple scattered seismic waves at the volcano, to measure very small changes in seismic velocity. So here is a paper from a few years ago showing if we look at, in this case, this is a cross correlation, but you could do this with earthquakes too. So ambient noise, we have positive cross correlation and negative cross correlation times. And when you look at the early part, this is 2 different times. It's very repeatable. And then later in the coda, the later part, then you get a very systematic decorrelation of the 2 waves because the multiple scattered waves are doing a better job at sampling the volcano. So here's just a few details of how we do the processing of the correlations. It's very standard for this type of measurement. But using this technique of coda wave interferometry from ambient noise, we can measure the very small velocity changes. And so in this case, when we apply this at Great Sitkin volcano, this is 3 years of ambient noise cross correlations. This is the different stations, so we cross correlate between 2 different stations. I'll show where these are on the next few slides. So normally, for many years, there's some small variation. This could be due to environmental effects like rainfall or snow. It's unclear. These are small. This is in a percent velocity change, so it's, almost 0.1%, very, very small. It's basically no signal. But then on August 1st, 2021 is when we see, when the dome begins to be extruded, there's a very distinctive velocity increase at the volcano. So as the dome comes out, all of a sudden, the seismic velocity increases by up to 0.5%. So, and this has been reported at Merapi volcano in Indonesia in previous papers. The opposite effect has been reported at Montserrat in the Caribbean, where the lava dome was destroyed and the velocity decreased. So anyway, at Great Sitkin, we have, for every station pair, and autocorrelation, we have one of these measurements. So we can look at all these different measurements around the island, although every pair shows this increase of different amounts. So here's an interesting correlation. So this is showing in the top plot from satellites, geologists can look and measure the volume of the dome. So this is on August 1st, the dome began to be extruded, and then every day they measure in good conditions the dome volume as it gets bigger and bigger. So it grew very fast in August 2021, and then it sort of asymptotes to 30 million cubic meters of total volume at the top of the mountain. And so that lava dome increase, here you can see this is this Coda wave interferometry measurement. At the same time, a clear increase, and then very steep at first, and then a smaller increase. So it's very closely related to the volume of the dome that's being extruded at the top of the volcano. So we can see a very good correlation in dome volume and seismic velocity. So the next question we wanted to look at was, where is the change happening? Naively, I thought the change should be right at the summit. That's where the dome is coming out. So, but we wanted to check, so we used a method that was first invented by Anne Obermann, who is a seismologist based in Switzerland now. So she showed how to invert these measurements to make a tomography image of where the changes are happening. So it was using these types of mathematical kernels and then solving a linear inverse problem where this is our measurements. We have this kernel, which is known, and then here's our unknowns. So it's a matrix inversion problem. So what we found, surprisingly, at Great Sitkin is, so here's the volcano, that's the summit, that's where the lava dome is coming out. But the change is off to the northwest. So that was surprising. I expected the change to be at the lava dome, but it's mostly on the northwestern part of the volcano. So you can see here, the average change we measured was around 0.5, but when you map it in tomography, here it's 0.8, over here it's much less, 0.1 or 0.2. So we see, here's some assumptions about the scattering properties, and we get a good fit. This is showing the fit of the measured change and the modeled change. So it's mostly on the northwestern side of the volcano. So why is that? So our interpretation was to look at the geological map of the volcano, and this is in a paper from 2003. It turns out the northwestern part of the volcano is very distinctive. It's shown here in hatch marks. That part of the volcano, some thousands of years ago, the edifice collapsed into the Bering Sea. So the volcano became so steep that the whole northwestern side of the volcano collapsed into the Bering Sea thousands of years ago. And so this whole section of the volcano has been filled in by newer volcanic lava flows over the past thousands of years. So this section of the volcano where the collapse was is very closely correlated with where this changes. So then the interpretation is, why is it on the northwestern side? This recent volcanic material is weaker, it's newer, it's younger, and it has a greater susceptibility to the applied stress of the lava dome. So think of it like in these new lava flows are cracks, and they close more easily when the stress of the lava dome is pressing on the edifice. So it means that the volcano is not homogeneous on all sides of the volcano. It's more susceptible to closing cracks on the northwestern side. So it's showing the complexity of the volcano itself. So this is similar to observation about 20 years ago at Merapi by Uli Wegler from Germany and co-authors. And there they looked at these similar Coda wave measurements, and they saw an increase of velocity during dome growth at Merapi in Indonesia. And then interestingly, they had even fewer stations than we do. They only had 3 stations, but they mention in the later part of the paper that they had no simple model for their observations because the volcano shows different behavior on its northeastern slope compared to its southern slope. So it very well may be at Merapi, they were also seeing that, you know, the volcano on a different side had different mechanical properties than other sides. So it's not sort of a uniform mechanical properties around the volcano, but this could be very similar to what they were reporting in their observations at Merapi. Okay, and then I think this is the last slide. And so there's an additional measurement that Anne Obermann based in Switzerland also talked about, which is decorrelation. And we haven't done a lot of research in this yet, but this is future work. When you do a cross correlation of ambient noise, you can get a time lag, but then you also get the correlation coefficients, which 1 minus the correlation coefficient is called decorrelation. So they showed, Anne Obermann and others, how to use it to do similar tomography of decorrelation. So we haven't done the tomography yet, but this quantity is measuring changing wave scattering rather than changing velocity. But here's a similar plot at Great Sicken where before the eruption, it's unchanging, a very similar decorrelation coefficient. And then when the eruption begins, we see a linear anomaly of the decorrelation. So in the future, we'll also apply tomography with a different kernel to these decorrelation measurements at Great Sicken to get more information about the subsurface properties. Oh, and then, sorry, one last slide. So just to emphasize this, these similar variations are observed during large earthquakes, but at the volcano, what's different is we see an increase instead of a decrease. For a large earthquake, it's usually a decrease of velocity, and then it heals over the course of months back to its normal value. That's what you see for large earthquakes. But for volcanoes, it increases, and then there's no healing. It just stays at the elevated velocity. Apparently, it has not yet decreased back to its earlier state. So there's differences with large earthquakes in the way that these types of observations are interpreted. All right, so this is the conclusion. Just first at Great Sicken, looking at these small seismic velocity changes correlated with the lava dome emplaced at the summit of the volcano. And so there's still future work, but we can see now that it's because of the different slopes of the volcano have different mechanical properties. And then going back to the first part of the talk, looking at the new Bancroft algorithm that includes both P and S waves, and we applied it to earthquakes at Trident. We also were able to delineate the upward migration of hypocenters at Trident during the beginning of its swarm. And then there could be possible future applications of this Bancroft algorithm because it's an analytical solution, so it's very, very fast. And with that, I thank you for your attention and love to take any questions. Thank you.
Thank you very much, Matthew. ¿Alguna pregunta? Paco.
Thank you, Matt, for your very, very nice talk, very inspiring talk. I was wondering about the Bancroft algorithm, how to introduce, and I see you are considering kind of constant linear gradient approximation with the rod mean square you did. So I was just wondering if it would be possible at least to have a improved version. It will be a dream to have a layer medium, but I think it will be possible. What do you think of improvements of this algorithm, and how easy it is to use for the Popo we have here?
Okay, thank you for the question. And so it's a good question. I didn't emphasize it, but the velocity can be any layer, one-dimensional layer type of velocity. Now, I've only so far looked at velocity that only increases. If there was a low velocity zone, then there can be ambiguity of the depth because the velocity has a multi-valued. But as long as it's increasing 1D, it should work. It doesn't need to be linear. It can be any layering. But then, I guess the first question would be, can it be also to one-dimensional velocity model that's multi-valued? I haven't looked at that yet. And then maybe, if there were a way to do it for three-dimensional variation, maybe that would be at each latitude, longitude, a different 1D model. That would take more work. But it's a very simple algorithm because it's analytical. It runs very fast, so I think it could be applied to different volcanoes, and I'm interested to try it at different volcanoes.
¿Alguna otra pregunta? Aquí en medio.
Thank you for your nice talk. I have a question regarding, have you measured how fast is it compared to the initial solution by hypo-inverse, the one that is the 5 kilometer?
Okay, so when you use that hypo-inverse, in hypo-inverse, it has, the user sets the initial guess. And at AVO, we set it for 5 kilometers depth because usually the earthquakes are in that depth, but it's very simple initial guess. So, I didn't show here, but there are cases where that's not a good initial guess, and hypo-inverse will fail to converge to a solution. So, I need to make some more tests with this, but the idea is with this better initial guess, it should put it close enough to the true solution that it will have a much better chance to converge. So in the examples here, I don't think there was a really good example of that lack of convergence. Even the 5 kilometer one eventually could find the location, but I can think of other situations in Alaska to test that it should show more clearly the advantages of having this better initial guess from Bancroft. But that is also for future work.
Thank you very much.
¿Alguien más? ¿Una pregunta? Marco.
Thank you, Matthew. Thank you, Matthew. It's quite interesting. Just one question. Did you try to use the Bancroft initial depth as initial depth for hypo-inverse to see if you find the same RMS, any changes in hypo-inverse? Because hypo-inverse is quite commonly used, and then you are showing that there are up to 5-10 kilometers of difference in the depth estimation, and this is quite important in volcanic monitoring.
A very good question. I may not have shown it here, but also for the future, hypo-inverse is written in Fortran, so we need to write a subroutine in Fortran to be part of hypo-inverse, and then it should, coding the subroutine and then include it in a new version of hypo-inverse that can use the Bancroft as the initial guess. So that right now it's still it's a research code, but the next step will be to make it for production, no longer research, so that it can be used in everyday locations by our analyst.
And it changes a lot the initial trial epicenter location?
Yeah, the epicenter from hypo-inverse is just the station with the earliest pick. So in one of the tests, it showed the Bancroft is able to get much closer to the catalog solution, which is, let's say, true. So it gets much closer. And so the epicenter should be the best determined. There may be, who knows, there may be some problems from time to time with the depth. That's usually much harder. But even if, I can imagine, even if the depth, if there's problems with that, the epicenter will be better than the hypo-inverse epicenter. But I've done some tests, and there's a lot of details, but I think you could at least use the Bancroft algorithm, which I think will be better than hypo-inverse like 99.99% of the time. And then the other time when it's not as good, then you can just use the hypo-inverse initial guess, which is what we've always been doing. So, there should be a way of just reverting to the usual way if for some reason the Bancroft algorithm doesn't work as well. So, but in most of the time it should be better.
Thank you.
Matthew, tell us a little bit about the maintenance of the seismic network. People live there or they travel from Anchorage. How many people work on these?
Yeah, great question. So at the whole in Anchorage, we have about 20 to 30 staff. And then we also in Fairbanks, there's about 10 to 20 staff. So it's both, I didn't show where Fairbanks is. Fairbanks is north of Anchorage by about 6 hours car. So there's all in total about 40 or 50 people at AVO. And of those, about 10 are field engineers. So yeah, their job is very exciting. It's in the summer from May 1st to October 1st. They go out to the Aleutian Islands and almost continuously to all the different volcanoes, and you have to fix solar panels, change batteries. But they're out, for most of the summer doing the field work. Now, myself, I'm not a field engineer, but in the summer for about 2 or 3 weeks, I will go out and help them. And other people who are not field engineers will usually go out for 2 to 3 weeks in the summer and help to do that. And that all that work is mainly with helicopters, so it can be pretty expensive. Although just last year they started for the first time to hike. To save money at Volcano. So that is also very physically exerting. So but there is, I think, they want to do as little helicopter flying as possible because helicopters are expensive. They can be somewhat dangerous, especially if you're flying over the ocean. And then also they emit fossil fuels. So we want to cut back on all those things in the future as much as we can.
Allá atrás. No, quédatelo tú, Denny, y yo doy este.
Thank you for your talk. I have a question, something you mentioned. So you have a quadratic equation, but then you have two. So at the end, you have 4 solutions. So how difficult it is for you to choose which one is the correct one?
It's a great question. So, yeah, in that case, there will be 4, so you have to find the one. So in the code currently, the 4 can come back. And in my experience, one of them will be this problem where it's happening, the origin time is after the picks. 2 other ones will be complex numbers that I've seen. And then 1 is the one you want. So what I do is I take the real part of all 4. Then I find which one is the best fitting and happens before the picks. I think is the logic right now. And so far, that has been a way of screening out to find that one. But I do want to do more testing before, to make sure that all the different possibilities can happen. And then there's also, the picks can have errors. So there could be noise. So that will, like you're saying, the precise logic to figure out which one of the 4 is the one you want, that is an important area of the algorithm.
Denny?
Yes, in the list of swarm that you show at the beginning, some of them finish with an eruption and some of them not. For the one without eruption, do you notice, what do you see about the depth of the seismicity? Is it kept at a certain depth? Or?
I'm trying to think now. It can vary, but I've seen them get, they can stop within 1 or 2 kilometers of the surface. So it can seemingly get very close. And so that is a very difficult question for
It's
volcanologists.
not 5 or 8 kilometers.
It can also be like that, but I've seen them also get very close. Like for example, just in the past month at Kilauea in Hawaii, there was a swarm in the southwestern rift zone, and I think there the dike, there was no eruption, but the dike became, from what I understand, very close. So the earthquakes, within a kilometer of the surface. But it's a big question that volcanologists have is, is this going to stop, or is it going to go all the way to an eruption? So when there's a crisis, that's the question everybody is asking to see, is this going to culminate in an eruption?
So it's not a good parameter to predict eruption.
Yeah, I think they call them, sometimes in the observatory, they call them failed eruptions. So it's for, I guess maybe the gas content of the magma is just not sufficient to break all the way. Oh. No, maybe unless the depth is 0. then well, or at the surface of the Earth. But no, it's not good. Maybe we do look at other things to predict, and one of them is how active the volcano is. So usually for a volcano that has been asleep for over 300 years, the earthquakes are going to need to be magnitude 3, magnitude 4 before it goes to eruption. If it's a volcano that's active every year, then it could erupt with very small earthquakes. Or sometimes in Alaska, there's some volcanoes that erupt with seemingly no earthquakes, which is also actually is one of the reasons for looking at coda waves. That could be another indicator of subsurface conditions at these volcanoes, which are very problematic.
Taking over the question of Denis, in your catalog that you showed over the time, which is the magnitude of completitude of your catalog? Changes over the time, or?
It does change, and at different volcanoes. So that was all the volcanoes. And at different volcanoes, it'll be different. The seismologists estimate every year completion magnitude, but we aim for, let's say, between 0 and 1. At a monitored volcano, you want to locate at least down to magnitude 1, and you ideally like to go to magnitude 0 to see those little volcanic earthquakes. So that's, I would, just to make a guess, over the whole AVO network, I would say it's 0.5 completeness magnitude.
Then the general trend of the increasing over the time of the seismicity is not related to the network performance or something like that. You think that it's
the increase of earthquakes. So that is due to the number of seismometers. So I showed that at the AGU, and somebody said to me to also, and I didn't do this, to show the number of seismic stations. So the number of seismic stations starts with like 10, and then by the end it's 300. So as you put out more seismometers, you measure more earthquakes.
Okay,
so but it's a good point to make. It's not an increase necessarily in seismicity, it's just being able to measure more earthquakes.
Matthew, thank you for your talk. I feel curious about, it's not as a specific topic of your talk, but as you show, you have had a lot of unrest in different volcanoes, you have a lot of volcanoes. So I wonder, how do you manage the hazard and risk in these cases and with this amount of volcanoes? I mean, do you have hazard maps, or how do you manage the situation? Because, well, you mentioned that the main threat is the airplanes, right? But how do you manage all these different unrests and different volcanoes?
No, it is very challenging. So you bring up like a part of the talk I didn't show about was hazard assessments. So at the Volcano Observatory, roughly speaking, half is, geophysical, real-time, seismic, deformation, infrasound, satellite observations. So we call that sort of the geophysics or real-time. But then the other half is hazard assessments, which is mostly geologists. And so they are making geological maps, and we don't yet have geological maps at all the volcanoes, so they're working at particular ones. And then there's some volcanoes, like there's 5 in Alaska that are considered the highest hazard, highest risk. And they're the ones that are near villages or cities. And so in that case, at one of those volcanoes, a hazard assessment and a geologic map was produced about 25 years ago. but then this year they want to go do improved new hazard assessment. So at the most important volcanoes, there's going back and improving the hazard assessment. So it's sort of like a iterative process that it has to be improved with time. And then also with the hazard assessments is outreach and community engagement. So then to go to the communities near the highest risk volcanoes and presenting it to the community so that everybody is aware of the hazards of the volcano. So that's, but it, as you say, it's, some of these geological maps, I'm not a geologist myself, but they can take a long time. Sometimes they can take 20, 30 years to finish all the questions. So it's an ongoing, process of geologic investigation.
Thank you.
Mm-hmm.
I have one question for somebody who is looking at the talk remotely. Is Dr. Ivan Granados, and he says, we assume that the velocity changes due to magmatic intrusions or water infiltration can be tracked by measuring delays at the coda of the cross correlations. But have you ever noticed also inner structure changes after large eruptions that delay not just the coda, but the ballistic waves?
Oh, this is a question from online?
Yeah.
Oh, okay. Oh, the ballistic waves. And who is asking the question?
Ivan Granados, doctor.
Oh, okay. So, the ballistic waves, I have seen, we haven't in Alaska tried this, but I would expect that the ballistic waves would have a more difficult time. But if the change is large enough, then you could see a change in the ballistic waves, but it would need a large change. The coda waves are nice because they bounce around the volcano. So a way I have of trying to explain this that I've heard actually somebody else a long time ago say is, say I was wearing say I have my shirt on right now, okay, and I, like a cord, like I want to wrap a cord up to put it away. So, say I'm not wearing a shirt, I do one wrap of the cord. Then I put on a long sleeve shirt and I do one wrap. And it comes to almost the same spot because the thickness of the shirt is only that much. But then if I do it here, and I do it like 100 times, and I come up to here, then I put on a long sleeve shirt and I do it 100 times, and instead of coming to here, I come to like here. So it's sort of, that's the multiple scattered waves are measuring that small change over and over and over again. So if it was a very thick, like a jacket, maybe you could see on one turn of the cord, but it would have to be a very large change. So it would have to be a very large eruption to see that, would be my guess.
Thank you.
¿Alguna otra pregunta? Sí, aquí.
Also, thank you for your talk. It was very interesting.
Thank you.
So I was thinking, at Great Sitkin, have you seen any evidence of deformation in this area where you're mapping your velocity anomaly?
That's a great question. So there have been, just in the last year, in the journal JGR, there was a publication of INSAR. And in that INSAR image, it was mostly at the summit. So that is, a question which, perhaps, the deformation was less in this northwestern part, but the cracks are just so more sensitive that they are closing. But from what I saw from the INSAR image, which I can't remember the first author, but it was in 2023 in JGR, they weren't from a Alaska Volcano Observatory, that, the deformation looked like you would expect for a volcano, like a bullseye. And the deformation was not so much inflation before the eruption, but deflation after the eruption. So, that dome being in place, pressing down on the surface and, deforming the surface of the Earth. But I was just asking somebody the other week at AVO, why is it that the INSAR doesn't look more on the northwestern side? So it must be even a more exaggerated version of this sensitivity to the closing of cracks that is on that side of the volcano. So it may take, in the future, we may put more seismometers out on the northwestern side to see in greater detail what exactly is happening. An alternative hypothesis that I don't personally, have as much confidence or would say is the magma chamber is to the northwest. But I don't think so. I don't think the magma chamber is offset to the northwest. I think the magma is coming from beneath the volcano. But some people have suggested that the magma chamber could be to the northwest. But that would be an alternative hypothesis. It's a great question.
¿Más preguntas? Si ya no hay preguntas, entonces, Paco.
I think you give very nice explanation for the stretching of the differences in the deep coda. But anyway, the variations you show and the variations that Michel Campillo shows large variability, and I always discuss how to reduce the uncertainty of this measurement, because the method of stretching is, you say, is a linear correction, like time. You stretch the time. Maybe there would be some chance to reduce the uncertainty. This is one little question.
It's a great question, and I can show a slide that is some of my thinking about this. But just one detail is, I know about, or I've heard about the stretching method, but this results I show is even more simpler method of multiple window. So it goes multiple windows into the coda and cross-correlating in the little window. So I think it's called multiple window time-lapse analysis. So it's a little bit different from the stretching method, but it should give the same result in principle. But it's maybe a more old-fashioned way of doing coda wave measurements. But I have collaborated with researchers at Purdue who use the stretching method, and they get similar results. So it is good to check. But I did have a additional slide that I didn't get the chance to show that. An additional slide which shows some of my thoughts. So just in the observatory, the way I look at it to assess confidence is, so this is at a different volcano, and this is from earthquakes. So this is in Alaska. In the last 3 years, we had out in the Aleutians, we had magnitude 7.8, 7.6, 8.2. So here's two stations. It's at a different volcano in Alaska. So when I look at it at the observatory, here in the top is the cross correlation, positive lag and negative lag. So what I want to see is both in the positive lag and in the negative lag. If one shows it and the other one doesn't, then I don't put confidence in it. But I also want to see it in the autocorrelation. So this is blue and black are the autocorrelations of the two stations, and I also want to see the result there. So I want to see it in 4 different ways for me to be confident of it. Otherwise, we see sometimes, one of the 4 shows it, and then it's like, I don't know, that's not so confident. I want to see it and be very sure of it. So in this case, magnitude 7.8, it produced a decrease. That's for earthquake shaking. And then it heals back over some months. And you can see it in the 2 cross correlations, negative and positive lag, and then also in these 2 autocorrelations. So that's like a practical way of trying to be confident of it.
Thank you.
Thank you very much, Matthew. Démosle un último aplauso a Matthew, por favor.
Oh, thank you.
Muchas gracias a todos y todas por su asistencia. Nos vemos en el siguiente seminario institucional. Que tengan buen fin de semana.